Hey folks, in this video we're going to talk about a post-hoc analysis for Anova, which is called Tukey's test. And this is something that you do after an Anova test, and let's see why. With Anova, we have this null hypothesis, right? And if there's a fourth group, you would indicate that. If there's a fifth group, you would just let the good times roll with the string of inequalities in the null hypothesis. But the alternative states that at least one of the population means is different. When the conclusion to an Anova test is to reject the null hypothesis, what we would say in our conclusion is that the data provides evidence that at least one of the population means is different. However, what the conclusion from Anova does not do is it does not indicate which of the means is different from the rest. If we're comparing three groups, and I'm going to kind of be brief here, there essentially is different pairs to consider. There's a comparison between group 1 and group 2, a comparison between group 1 and group 3, and there's one more, group 2 versus group 3. So there's sort of like different pairs that can be considered, and if at least one, maybe it's just one, at least one of the population means is different, then we would see that difference be expressed in some way throughout these pairs. Now, if you throw in a fourth group, you have more pairings to consider, so I'm just going to stick to 3 for right now. Now, for instance, just to elaborate a tad more, suppose it was group 3 that was different, and group 1 and group 2 were not significantly different. So if group 3 stood out, we would see when we compared group 3 with group 1 that we would see some indication of that difference. Same thing with group 3 versus group 2. Now, like I said, if group 1 and group 2 were not significantly different, then we wouldn't see any indication of that. Now, how could we check which group or groups appears to have a population mean that is different from the rest? We could do this with a confidence interval for the difference in means. And we would do it for each of these pairings. So here we would have a confidence interval for the means between group 1 and group 2. Here we would check the confidence interval between group 1 and group 3. And here we would check the confidence interval for the difference between 2 versus 3. When I say how do we check, we would be looking for that number 0, right? And we would say that if the confidence interval contains 0, then that indicates no significant difference. And on the flip side, if the confidence interval does not contain 0, then that does indicate a significant difference between the two population means, or at least the evidence seems to suggest that. And so this is essentially what this Tukey's test does, is it's going to break up all the pairs. If you've got 3 groups, then there's going to be 3 pairs. And it's going to do a confidence interval for each of those pairs. And it's a way to look, hey, if 0 is in the interval or not, that's going to be an indication of which group seems to suggest it has a significantly different population mean from the rest. So going along with my previous example here, if group 3 was the one that seems to have a significantly different population mean, we would see 0 in this first one only. We would not see 0 in these two. And so to get out of the theory realm here, I want to actually give you an example with data, and we'll take a look at it in R. But before we do that, there's another side to this coin. Right, this is usually performed when we reject the null hypothesis from Anova. If the analysis of variance test does not result in a rejection of the null hypothesis, then all of these pairwise comparisons will result in confidence intervals that all contain 0. So that's something worth noting. Usually this Tukey's post-hoc test is generally performed after a rejection of the null hypothesis to further analyze, oh, cool, a difference occurred. Anova doesn't tell me where that difference occurred. It's this Tukey's test that's going to hone in on which group or which groups might have that different population mean. So we'll also kind of run this in this other scenario, but what we will end up seeing is that a non-rejection will still have all these confidence intervals to look at, but they would all contain 0. So I'm going to open up R and I'm going to get some data sets ready, and we'll see this play out. All right, folks, this is the data set we looked at in the previous video where we had the weight gain in different lambs across 3 different diets. And in this example from the previous video, we saw how to do analysis of variance in R. We got this Anova table, and our conclusion was that, hey, look at that p-value, that's bigger than any alpha that is typically used, so we do not reject the null hypothesis, indicating there is not sufficient evidence that at least one of the mean weight gains is different across the various diets. So we usually would not do a Tukey's post-hoc test here because we haven't detected a significant difference anywhere. But you can still crunch the numbers, and I think it's still kind of a worthwhile experience. Let me show you how it's done. So this is, I'm going to give it a name. I'm going to call it post-lamb because it's a post test. And the syntax for this command, or it's Tukey HSD. I think that stands for honest significant difference. I forget. But what I'm going to put into this Tukey command is the name I gave when I did the AOV, the analysis of variance. So I'm going to pop into here, sheep. Sweet. Now, if I just ask it to look at post-lamb, like I just typed post-lamb, that's fine. It's going to give you a lot of output, and I think for us what might be even better is to plot this. What it's going to do is actually plot the 3 pairwise confidence intervals. So this is going to show the 3 pairwise confidence intervals for the differences in the mean weight gains. So it should get us a graph. Here it is. And something that we're going to look at here is, because there was no significant difference anywhere in these three diets with respect to the population means, check out, here's the number 0. And what this is doing, it's not the most high-tech, hi-fi image here, but this is showing a confidence interval on a number line. And here, the one on the bottom is the confidence interval for the difference in means between diets 2 and 3, between diets 2 and 1, and 3 and 1. It's showing all of those possible pairings. And so you can kind of see, like, hey, this confidence interval, it appears to be like, I don't know, -9 to like a +11 or something like that. And somewhere in there, negative number, positive number is a 0. And same thing with all these other two confidence intervals. They span from the lower bound of a negative number to a upper bound of a positive number. So all three of these contain 0, as we would expect when we fail to reject the null hypothesis. So I'll put a little note here. All three confidence intervals for the difference in mean weight gains, they all contain 0, which is as expected when Anova results in a non-rejection of the null hypothesis. Let's look at another example now in which Anova does result in a rejection. And we'll see this same image, but we'll see how 0 plays a role in that case. Okay, I've got another R open up here. Okay, I have opened up a new R here with a new data set to show you. And we saw this data set in a previous video as well, in which this was our intro to Anova. And here I had this graph in a previous video to illustrate these three treatments have values in which they are so overwhelmingly different that most certainly we would characterize that difference being present in their population means as well. And here I have the code for this graph. You're going to make one of these in lab as well, so you don't got to worry too much about that, but you will see that again. And we saw this in the previous video. This was case 1, and we did the analysis of variance of the values in case 1 across the different groups. And we saw this super duper small p-value indicating a rejection of the null hypothesis. And so we're going to do this Tukey's test. What a name, huh? And I want to anticipate what we are going to see. We have 3 groups again, 3 treatments. So we're going to see 3 pairwise confidence intervals. And what we're going to see is that, gosh, it appears that they are all different from one another, right? We're going to see that none of them, we're anticipating that none of the confidence intervals for the difference in population means will contain 0. None of them. So the code, just like we did with the lambs here, I'm going to call this, you can call it anything you want, but I like calling it post, and this was case 1. and we're doing this Tukey HSD, and I want to input into the Tukey command the same thing that I called my AOV table. So I'm going to call that case 1. And now I can plot the post.case1. Okay, let's take a look at this. I got to make this kind of big because the names of the groups were a treatment, so it just has a lot of letters. So I'm just trying to fit those all in here. And let's look. So we've got treatment 1 versus treatment 2, treatment 1 versus treatment 3, and then 2 versus 3. So those are the 3 possible pairs. And let's look at this. These confidence intervals, they're kind of very tight knit, right? Because we didn't see much spread in those samples. And so if we look at this horizontal axis, 0 isn't even on the axis. R kind of formats it for your view and pleasure. And we can definitely see that none of these confidence intervals, lower bound, upper bound, none of them are spanning into the positive realm over here, right? So this 0, not in there. 0, not in there. 0, not in there. If I wanted 0 to be graphed, and it's not going to change the location of these confidence intervals, but if I wanted to see 0 in this image on this horizontal axis, I could ask R to make my X limits from, let's see, I'm going to make a vector. Let's do it from -10 to a positive number, maybe like a 2. So now we've got 0 as a visual reference here, and we can definitely see that none of those confidence intervals contain 0. So that's indicating that the data provides evidence that the population mean is different for every group across every other group. So population mean 1 is different from 2, population mean 1 is different from 3, and population mean 2 is different from 3. And that's what the data seems to suggest here. So this is the Tukey's post-hoc test for Anova, and we will do this in lab 11. So we'll do this in lab 11. Have a good one.